In this series of videos, I'm going to go over the solutions for Kinetics Assignment 3. So, here are rate laws for free radical polymerizations, and we'll use those in several of the problems. So the first problem, if an AIBN, a common free radical initiator, is used to initiate the polymerization of methyl methacrylate and benzene, and we're given the initial initiator concentration, the initial monomer concentration. Our efficiency is 100%, so F equals 1. What is the initial rate of polymerization? And then we're given the rate constants we need. Okay, this is sort of as straightforward and classic a kinetics problem as we can do. So, this is a really key word, initial, the initial rate of polymerization. Okay, so we want to calculate RP, the rate of polymerization, but it's the initial rate of polymerization. So we don't have to integrate, right? Because it's nothing with respect to time. Okay, so let's start working on this problem. Okay, so we want to find our initial rate of polymerization, and we know we have initial conditions. So what do we assume when we have initial conditions? This is really important. We're going to assume that our monomer concentration is approximately equal to our initial monomer concentration, and our initiator concentration is approximately equal to our initial initiator concentration. Why do we like initial conditions? No integration. We don't have to separate the variables and integrate because nothing's changing with time. The reaction has just started. Okay, so we need to remember that our rate of polymerization equals our rate of propagation. We get that from our rate laws, which is equal to Kp radical concentration times the monomer concentration. Now, of course, we don't know the radical concentration, so hopefully you remember what we need to do. We need to make the steady state assumption. The steady state assumption assumes that the radical concentration is not changing with time. If the radical concentration is not changing with time, Ri has to equal RT. When we form a radical, we have to kill a radical. Otherwise, radical concentration will change. So then we just look at our list and we see that Ri equals 2F Kd times the initiator concentration. And RT, the rate of termination, equals 2 Kt times the radical concentration squared. And we solve for the radical concentration. FKD, initiator concentration, divided by KT, all to the 1/2 power. Okay, we're most of the way there. This is not too hard a problem. Okay, now I just need to plug this back in here. Okay, so I've got Kp times FKD, initiator concentration, over Kt to the 1/2 power times the monomer concentration. Okay. All right. Now we can start plugging in the numbers, my least favorite part. Okay, so let's do that. We've got Kp equals 515 inverse molar inverse seconds. Let's do the brackets. We've got F equals 1 and it's unitless times Kd 10 to the minus 5 inverse seconds for units times the monomer, the initiator concentration, 0.02 molar, divided by 2.55 times 10 to the 7th inverse molar inverse seconds to the 1/2 power times 2 molar. Okay. All right, now, before I plug that in my calculator, I am going to do a unit check, okay? So I'm just going to do a unit check over here. Okay, so I've got inverse molar, inverse seconds. Okay, and I'm going to write this on a single line. So I've got inverse seconds, molar, times inverse, right? So that's another molar, and then the inverse of an inverse is the straight up, okay, times molar. Okay, and that gives me, right, if this all, 1/2 power, okay, so that comes out to molar per second, which is right, okay, because all of our rates should be in concentration per unit time, okay. The other thing, because this is complicated going into the calculator, I like to just do an order of magnitude check when I've got all these minus 10 to the minus 5, 10 to the 7th, okay. So let's see, I've got, if I just do an order of magnitude check, that 515 is 10 squared. This is minus 5 minus 7 divided by minus 7, so I've got 10 to the minus 14 to the 1/2 power times 10 to the 0, right, or 1, and so that's 10 to the minus 7, so I think my answer should be around 10 to the minus 5. Okay, I just do that as to see if what I'm going to get in my calculator makes sense. Okay, but now if I plug that all into my calculator and I cancel all my units, I get 8.4 times 10 to the minus 5 molar per second, which seems pretty slow, but this concentration, I believe, is quite low for a free radical polymerization, and it's per second. So remember how moles is very big, so moles per liter per second. And if we do this out, if we multiply by 60 seconds and 60 minutes to get our answer in terms of hours, it's 0.3 molar per hour. Still seems slow, right? It seems like a slow reaction. But I believe I got all I believe these are all real rate constants, so I think that is correct. But again, I might have made a mistake with my calculator. Okay, now let's quickly look at problem 2. Problem 2, in an addition polymerization, the kinetic chain length is the number of monomer molecules reacted for a single initiator radical produced. It may be expressed quantitatively as the rate of propagation to the rate of initiation. The kinetic chain length is Rp over Ri. And remember, this would be given to you on an exam. You don't have to memorize that. If termination is by combination, the degree of polymerization is, hopefully you remember that, 100% by termination, it's 2 times the kinetic chain length. Okay. And we will come back, I will stop the video and come back with problem 3.